Assalamualaikum and good afternoon to our lecturer, Madam Asindayanti. We are from Group A3 and today we will be presenting on the topic applying thermodynamics to improve solar. To begin, let me briefly introduce our group members and their roles in the presentation. Firstly, it's me, it's Muhammad Hazim Akmal bin Abdul Hadi. Second, my group members is Lydia Farhana binti Aidil Firhan. Third is Nur Fatin Umaira binti Muhammad Farid. And the last group member is Mawada binti Zulkifli. Next, let's begin to the objective. The objective of the study is to explore how thermodynamics principles can enhance the efficiency and sustainability of solar. This present content of introduction, thermodynamics principle, industrial application, challenge and solution, case study and data analysis, solution, technological advancement, and conclusion. Next, we go through introduction. Based on principles of thermodynamics, solar energy systems are designed to convert sunlight into usable energy such as heat or electricity. This system plays a crucial role in promoting clean and renewable energy solutions. Thermodynamics allows us to analyze how energy is transferred, transformed, and lost in the system, helping improve their performance and efficiency. In this presentation, we will explore the type of solar system, how they operate, and common thermodynamic challenge they face. The common challenge of the solar system is high initial cost, dependent on the weather conditions, low energy density, thermal energy losses, and efficiency limitation. Next, we go to the thermodynamic principle.
Moving on to a thermodynamic principle. How was the first law of thermodynamics was applied? Okay, first of all, the definition of the first law is energy cannot be created nor destroyed. It only converted from one another to form other. Okay, the application is when the sun hits the solar panel, the solar radiant energy converts into electrical energy. In the solar thermal system, the sunlight converts it into a thermal energy or known as heat. In this law, the total amount of energy remains constant although the form changes. Okay, for the example is, the light from the sun was absorbed by a black surface from the solar panel, and the absorbed hits the water heater. Black surface tends to absorb more because it has a greater portion of the electromagnetic radiation that falls on them, converting it into a thermal energy. One, how second law thermodynamic was applied to solar energy. First of all, the definition of the second law, thermodynamic, is energy conversion never fully efficient and some of the energy always lost its heat, and it resulting in increasing entropy. The application of the second law is when the solar panel converts the sunlight to electricity, it doesn't require all of the sunlight convert, but there's a lot of heat was lost. Meanwhile, the solar thermal collectors was also suffer heat losses to environment. Typically, some of the energy was useful and fully converted. Meanwhile, some of it dissipated and cannot fully converted into a useful work. Okay, for the example, a photovoltaic cell might only convert 20% of the solar energy it received to electricity. The rest becomes heat or is
We
reflected.
jump to the industrial application. So how the thermodynamic applies in real world industry. For industrial application, I choose three, which is the first one electricity and industrial heat, the next one is process heat, and the lastly is thermodynamic solar panels. Okay, so for the first one, the example I use is CSP, stand for concentrated solar panels. It uses mirror to concentrate sunlight to generate a high temperature heat. Next one is example I use is parabolic. So it uses parabolic through collectors to get the solar energy and heat water and air. And lastly is thermodynamic solar panels. So it combines element of solar thermal and air sources for heat pump technology.
Alright, so for the next slide is we're gonna talking about challenge and the solutions. Energy conversion efficiency state when sunlight energy is converted into electricity or heat, not all of the energy can be fully utilized, which means the energy conversion process has limited efficiency. For example, a typical solar panel can only convert about 50% to 22% of light energy into electricity. The rest is lost as heat or cannot be absorbed. In addition, there is thermodynamics, which is the law of physics that governs the conversion of energy. The second law of thermodynamics states in every energy conversion process, there must be energy loss. This makes it impossible to achieve 100% efficiency. Therefore, although solar energy has great potential, we are still bound by efficiency and natural laws in its use.
Next is thermodynamic limitation on solar panel. First of all is heat loss. Whenever we convert sunlight to electricity or heat, some energy is always lost. In this matter, we cannot avoid it because it is a natural rules which no energy system is 100% efficient. Next is Carnot limit, specific for solar system thermal. Using sunlight to heat something like water or gas, then use that heat to make electricity, the maximum efficiency depends on temperature. Even with the best solar technology, we can't convert all sunlight into energy because physics says that there will always be some loss. That's the thermodynamics limitation. But we have the solution for the limitation, which is we developing more advanced solar panel technology, such as multi-junction solar cells that can absorb more types of sunlight and increase efficiency to over 40%. Other than that, we use concentrated solar power, CSP, to increase operating temperatures and make the system more efficient, although it is still limited by the laws of thermodynamics. And the last one is innovation in new materials such as perovskite, that also very promising because they are cheap and can achieve high efficiency.
So, next one is the case study I choose for support our analysis. So, for the first one, it based on the industrial application. So, for electricity and industrial heat, I choose the Ivanpah Solar Electric Generating System. So, it located in California. So, this company use CSP to generate electricity. So, the achievement is they generate more than 392 megawatt of electricity. And the next one is processed heat. So I choose Hudson Agro Product. It located in India. So this company used the parabolic tree collectors as a type of solar thermal. So it shows a successful optimization because parabolic improve energy conversion efficiency. It's obey to the first and second law of thermodynamics. So lastly, the thermodynamic solar panel. So the case study I choose is performance of PV panels in hot climate Malaysia. So PV is stand for photovoltaic. So it's combination of PV and heat pump. So these solar PV panels generate electricity so it can directly power to heat pump compressor. For example, household with solar panels on the
Moving on to social and technological advancement, improving solar efficiency. There are four main points that I would like to point out. Okay, the first one is use a high efficiency solar cells. We could upgrade to a monocrystalline or multi-junction cells, which offer higher energy conversion rates. They are between 20% to 40%, and it also considered as a promising new technology. The second one is keep panels clean and well maintained. Dirt, dust, and bird droppings may be one of the reasons that could reduce the light absorption. So we need to have a clean panels to maintain a maximum surface exposure. The third one is use a cooling system to prevent overheating. As we all know, solar panels lose efficiency as they heat up. We could use a passive cooling known as air vents or active cooling to regulate the temperature. Lastly, we could install a solar trackers to follow the sun. We could use a single or dual axis trackers to follow the sun path. The reason why is it could increases the sunlight exposure and also can boost up output compared to fixed panels. For improving sustainability, there are four main points as well. Okay, the first one is support solar panel recycling. We could support by establish a solar panel recycling programs to recover silicon, glass, and metals. Second one is choose a eco-friendly materials and production. By choosing a manufacturers that use low toxicity materials and clean production method, it could reduce dependence on rare earth or toxic substances. Second one is combining with other renewable such as hybrid system. We could combine with wind, hydro, or biomass for reliability. And also we could use a smart grid tech to balance a supply and demand efficiently. Lastly is we could use a solar integrated building system, which is BIPV, building integrated photovoltaics in roofs, facades, or windows. This design could maximize passive solar heating and daylighting.
For conclusion, if thermodynamics provide the scientific foundation for designing and optimizing solar energy systems. Engineers can improve the efficiency, reliability, and performance of solar technologies by applying the laws of energy conversion and entropy. Thermodynamics principle help to solve the challenge like energy losses and storage limitation. Also make an innovation for solar system in future.